Hi there, physics fans. I hope you're staying safe and healthy. Today I want to talk about one of the most elusive particles in nature. I'm especially enthusiastic about them because Fermilab, the laboratory that hosts this YouTube channel, is the world's flagship neutrino laboratory. Neutrinos have surprised scientists again and again over the years, and I'm going to tell you about them in today's episode of Subatomic Stories. The story of neutrinos begins in the early 1900s, shortly after radioactivity was discovered. A certain type of radioactivity seemed to violate the law of conservation of energy. In 1930, Wolfgang Pauli proposed what is now called the neutrino, a low-mass particle that interacted only via the weak force. Because it interacted only via the weak force, it took a quarter century for scientists to discover it. In 1956, physicists Clyde Cohen and Frederick Rains used a nuclear reactor to discover the neutrino. Initially, they wanted to use a nuclear explosion for their experiment, but cooler heads prevailed. Instead, they put their detector near a nuclear reactor and repeatedly turned it on and off and saw that neutrinos were emitted by the reactions inside the reactor. While scientists knew that neutrinos were created in many particle collisions, they thought that there was only one kind of neutrino until 1962, when an experiment at Brookhaven National Lab showed that there were more than one. We now know that each charged lepton has a companion neutrino, so we have the electron neutrino, the muon neutrino, and the tau neutrino. The tau neutrino was the third subatomic particle discovered at Fermilab, and its discovery was announced in 2000. The existence of the neutrino and the fact that there are multiple neutrinos were both surprises, but the neutrinos were just getting started. In the 1960s, chemist Ray Davis was trying to measure how many electron neutrinos came from the biggest nuclear reactor around, the Sun. Using an Olympic swimming pool's worth of dry cleaning fluid, he found that he observed only about a third of what was predicted. Another set of experiments were trying to measure neutrinos made in the atmosphere when highly energetic protons from outer space slammed into the Earth. These were muon neutrinos, and huge underground detectors made measurements which, again, didn't agree with predictions. One possible explanation for the discrepancies was that the neutrinos were changing their identity, with electron neutrinos becoming muon neutrinos and vice versa, kind of like a cat becoming a jaguar and back again. This behavior is called neutrino oscillation, and it's unique among subatomic particles. Between 1998 and 2001, researchers proved that neutrino oscillations were real. The biggest experiment was a huge underground tank of water, and I mean huge. It was 50,000 tons. Now that we know that neutrino oscillation is a thing, researchers can make beams of neutrinos to study the effect in more detail. And that's what Fermilab is doing. In spite of already being the world's premier accelerator-based neutrino physics laboratory, we're kicking it up a notch with a big increase in the intensity of the neutrino beam and the DUNE Experiment located in South Dakota. We will shoot beams of neutrinos through the Earth and study neutrino oscillation. The experiment will explore a theory called Leptogenesis. This theory could explain why our universe is made of matter, which, when you think about it, seems like a silly question. Leptogenesis is a complicated topic, and if you're interested, I made a long video about it, and I put a link in the description. In fact, neutrinos are so interesting that I've made many longer videos about all sorts of neutrino topics. They all go into more details about everything I've mentioned here. I think you'll find them to be interesting. Neutrinos are interesting particles and have surprised scientists more than once and might do it again. They're just worth reading about. So that's all the time we have to talk about neutrinos. In our next episode, we'll talk about the known forces. There's a lot to learn about them. See you soon. So, it's time for questions. Like always, there were so many good questions that it's hard to pick, but pick I did, and here we go. Keep them coming. Studio 47 reminds us to thank everyone involved in making these videos. And that's absolutely right. While I'm the public face of many of the Fermilab YouTube videos, they wouldn't be possible without the absolutely invaluable contribution of Ian Crass, the producer of all my videos. Take a bow, Ian.
Hey, what's up?
And also a huge shout out to the other hardworking people in the Fermilab Office of Communication. Eddie Roski asks, if matter and antimatter quarks annihilate, why are there mesons? That's a good question. In episode 3, I talked about the mesons, which consist of a quark and antimatter quark pair. Since matter and antimatter annihilate, what's up with that? Well, actually, mesons aren't stable. They decay very fast, and they do so very quickly. For instance, a neutral pi meson, which consists of an up and antimatter up quark, or down antimatter down quark, the two quarks annihilate in 84 quintillionths of a second. Even the longest lived meson, called the pi plus or pi minus meson, lives for only 28 billionths of a second. That sounds crazy short, but it's actually pretty long in the particle world. It's so long because the pi plus meson consists of an up quark and a down antimatter quark. Those two quarks can't annihilate one another. In order for the quark to decay, it first needs one of them to change their identity, like having the down antimatter quark turn into an up antimatter quark. Then it can annihilate easily. The only way that can occur is via the weak force, and the weak force is, well, weak. It takes time. If you're interested in learning why the weak force is weak, I talk about that in one of my longer videos. You should check it out. Billy Bob asks if an electron can smash into a proton. The answer is yes. Researchers do it all the time. It's called deep inelastic scattering. They use a particle accelerator to shoot a very high-energy electron at a proton. The electron actually goes inside the proton and knocks into a quark. That quark bangs into other quarks, and the electron loses energy and shoots back out of the proton. Researchers then measure the amount of energy the electron loses and use that to figure out a lot about the quarks. We learned the amount of energy quarks have inside the electron. We learned about their charge and spin and all sorts of stuff. In fact, it's through this deep inelastic scattering of electrons into protons that we determined a lot of the quark's properties. Good question. Debashish Mohapatra asks why the Pauli exclusion principle only applies to leptons. Well, actually, it doesn't. It also applies to the quarks. It applies to any of a class of particles called fermions, which have half-integer spin. So spin 1/2, spin 3/2, and so on. The Pauli exclusion principle says that no two identical fermions can exist in the same place at the same time. It's why atomic orbitals can have no more than 2 electrons in them. Because the Pauli principle applies to quarks, that's what led researchers to realize that quarks had to have 3 different strong force charges. After all, if a baryon had 3 down quarks in it, all with the same electrical charge and spin, something had to be different about them. The idea of color was imagined, and it was only later that scientists realized that this color thing was actually the charge of the strong force. DG notes that they leapt on the chance to watch the video when it was released. Something tells me that he or she and I have a similar sense of humor. I'm very sorry for them. I'm told that doctors are developing a treatment for that, but it could be incurable. Sorry about that. Delwood Barker asks why there are only 3 generations of quarks and leptons and not an infinite hierarchy. Actually, nobody knows. In fact, nobody knows that the hierarchy isn't infinite. What we do know is that Z bosons, which are particles of the weak force, decay into exactly 3 different kinds of neutrinos. Exactly 3. So, since the neutrino pair with charged leptons and the charged leptons seem to pair with the quarks, it seems that there are only 3 distinct generations. Of course, if it turns out that there is a 4th generation of neutrinos, then there could be more quarks too. The only way that could happen is if the 4th generation of neutrinos are extremely heavy, about 10 times heavier than the bottom quark. And there's no evidence for this, and trust me, we've looked. So the short answer is we don't know why there are 3 generations. It's an open question. Martin Heermans asks, how, when you squeeze an electron and proton together, you get a neutron? Hi, Martin. Interesting question. That's how you get a neutron star, for example. Here's how it works. It is all because of the weak force, because the weak force can change the identity of particles. So the electron emits a negative W boson and turns it into a neutrino. It has to be a negative W boson to conserve charge. The neutrino then just escapes. The W boson then hits one of the up quarks in the proton and converts it into a down quark. We see that the charges work out okay because a positive 2/3 up quark plus a -1 W boson equals -1/3, which is what a down quark has. Remember that the proton is an up-up-down quark particle, and if you convert one of the ups into a down, you have an up-down-down particle, which is a neutron, so easy peasy. Captain 777 Harris asks if they serve chicken burritos at the Fermilab Cafe. I think the answer is no. I don't remember them ever serving any kind of burritos at all. But I can tell you that Francisco, the guy at the grill who makes some really incredible chicken quesadillas. If you're ever at Fermilab and he's making them that day, get him. You won't regret it. But now you made me all hungry, so that means it's lunchtime, and it means that we're out of time for questions. If you've enjoyed the video, please be sure to like it, and of course subscribe to the channel and share it on social media. You owe it to your friends. In our next video, I'm going to talk about how subatomic forces work, including some analogies that simplify some very challenging physics. Are you excited? I'm excited. And of course I'm excited, because learning new physics is awesome. After all, even at home, physics is everything.